So let's go to Vivado and implement this particular state diagram or this particular debouncer. So what you do see here is I wrote that because it's pretty on the long side, but it's mechanical. But I wrote it for you and I have posted this code so you get to read it. I'm just gonna go quickly through it. So what you see is the input is a switch, and of course I need a reset and a clock because it's a sequential circuit, and the output is a debounced output. That's what we're looking at. So basically we have an input switch and a debounced output. That's what we care about. The rest are it's like simple reset and clock. So you do see in here is I have instantiated something, and that is basically the modulo M counter. It's actually the same modulo M counter that we have seen before. It's the same exact one. I did not change this one at all actually. Okay, I don't care about its Q value. I just care about its tick, and that's what we're going to be doing. So I instantiated it, and you can see that I'm actually after a 10 millisecond. That's what I really want. So 10 millisecond divided by 10 nanosecond, you convert it so that basically both of them are the same units. You divide them, you get to see that the value is 1 million. So what this is telling me is if you're operating at a clock frequency that is 100 megahertz or the clock period is 10 nanosecond, you need a million count to get to 10 millisecond. So read these comments and see how I actually calculated it, but I instantiated that particular counter and I wanted it to count for a million count, and these million counts will give me the tick. And as you can see in here, the .q is the output. I basically didn't connect it to anything because I don't care about the value of that. I'm just using it as a timer, and that timer basically will generate that M tick. It's the same M tick that we talked about. It's external to this, it's external to that. I just instantiated it within it because I'm using it. And as you can see in here, you will see that basically it's part of the tick. The tick is actually under a modulo. I'll talk about the top file shortly. Okay, and then I started, it's basically a finite state machines. I started by the enum, the type def. I basically wrote all 8 states, and then I defined the variable, and then I separated the state register, like how to update it. And then this one here is just a follow of what happened in that particular state diagram. You can read it shortly, but it's really basically a case statement that tells me what's the current state. Is it 0? Is it weight 1 under 1? And it's like, and then I'm asking if the switch is asserted, if the mtick is asserted, and based on that, I'm moving between states. So you can see all of these. I basically follow the chances are going to make a mistake. I probably made a mistake while I was developing it, but anyway, you get the idea. And then what I have is a more output. So this is how convenient it is now because I didn't combine the output in here and I put it separately. You're going to see that it's as simple as saying, well, according to what we have seen, I think this is here, the output is asserted, okay, whenever we're in this state, this state, this state, or this state, one of these 4, okay, 1, 2, and 3, and 4. And that's pretty much it. So this is basically how a debouncer is. Okay, so let's test it. So what I did is I created a top file, and in that top file, I did the following. And its purpose of the top file is actually just to instantiate everything under it and basically connect it to the FPGA board. So in the top file, I created something that has a switch, a reset and a clock, and a debounce. But what I added is, I added this one here, which is JA. Well, JA is one of the PMOD input on the FPGA. And the reason why is because I want to take the switch and the debounced output completely out of the circuit so we get to see it on a scope, okay? But as you can see, all I did in that top file is then instantiated the debouncer. I connected all the signals to it, and I'm just basically exposing the switch and the debounce to these particular pins, which are 1 and 2. So let's go and see it on the FPGA. So I'll generate the bit stream and upload it to the FPGA, and we'll see what happens. Okay, so the bit stream has been generated and it is actually now on the FPGA board. So what I did is I connected the reset to the middle button, and my switch, the bouncy one, is actually the bottom one, and I connected the debounced output to the LED. So you can see that I'm actually pressing it several times and the LED is being lit. Of course, I can't see the debounce, so what I need to do is I need to connect it to some sort of a scope. So what I have is I have one of these analog discovery 2 in here, okay, the Vigilant. It's like, it's a multifunctional USB thingy. It's useful. If you have one, you can use it. What you can see is I connected this is the JA, which is jumper A, okay, usually you connect PMODs to it or externals. So what I did is I exposed JA1 and 2 in here, and I have connected the ground as well. And the reason why I'm doing that is because I want to see the waveform. So let me just show you what I mean by the waveform. So here's what we have. So I will show you a little bit of the what I'm doing. So I'll be pressing, and you can now see a couple of things. So you do see something in yellow and something in red, in blue, sorry. So let me press a bunch of them and just show you. So, and then I'm gonna stop it. Okay, so what I was doing is basically based on the presses I have, you will get different outputs. Okay, so let me just remove this and let's see. So what you do see here, the yellow is actually my input, which is actually my switch, and the blue is actually my output, which is the debounce version. You still can't see it, and the reason probably why is because I'm taking that output to the jumper. It's not really the output that you get from the switch directly. It's actually the output that passed by the FPGA, and then the FPGA routed it out. So you were not going to see the debounce very clearly. Anyway, or it could be also my scope is not very clear in here because it's a USB version. But what I care about in this graph is actually the delay. So what I want to do is I want to see, does it actually make sense to delay? Let's see. So here's the yellow. Here's, for example, at this point, I will actually calculate how long did it take. And according to this particular delta X is 22 milliseconds. That's actually according to specs. It's more than 20. Okay, I'll do it one more time in here. Okay, I'm going to do that in here. And there you go. Well, I guess I did a little bit like longer here. It's still, this one is from here to probably here. It's about 28 milliseconds. You get to see the idea. It's usually between 20 to 30. You're not gonna get 31 or something. Whatever I did was I did it basically in the wrong position, but you get the idea. All of them are not exactly the same, but they're within spec. Though this one is 27. And the blue output is usually what we get as basically the bounce output.